Now we are going to prove this claim using something called structural induction. Okay, it's again मैं disclaimer कर रहा हूँ. In my opinion, it's the same induction जो हम करते आ रहे हैं. Okay, इसमें कोई फर्क नहीं है. But it's just fancy name for sort of applying it on a structurally defined structures. Okay, sorry, recursively defined structures. My bad. Okay, here's the claim. The claim is okay, मैंने अब ट्रेस में कुछ चीजें आपको बतानी थी जो मैंने अभी नहीं बताई आपको. Okay, so the number of the nodes in a binary tree, इनको हम vertices भी कहते हैं. Okay, these are vertices. एक node को हम एक vertex कहते हैं. Okay, so for example, let me pick up a highlighter. So for example, ये वाला जो हमारे पास tree है, इस ट्री में हमारे पास दो नोड्स हैं, एक ये है और एक ये है. ओके, we'll say we have two vertices. Okay, so in this case हमारे पास 1 2 and 3, so हमारे पास 3 vertices हैं. इस केस में हमारे पास 1 2 और 3 vertices हैं. Okay, so these are nodes and vertices. ये जो आपके पास arrow segments हैं, इनको हम edges कहते हैं. So these are edges. And you can also count them. So for example, in this case, there are 1, 2, and 3. Sorry, 1 and 2. So the edge set has size 2. The vertex has size 3. So in this case, 1, 2, edge size has size 2. Okay. So ऊपर वाले case में edge set has size 1. Okay. यहाँ पे vertex set has size 1. The edge set has size 0. यहाँ पे vertex set has size 0. The edge set also has size 0. Okay, so let's see. What does our claim say, and let's see how do we prove it. The claim says.
एक सवाल है कि the empty binary tree which you defined, उसके ऊपर अगर कोई एक arrow जा रहा हो, because we are saying कि उस पे arrow जा रहा है लेकिन वहाँ पे कुछ है नहीं, तो उस arrow को भी हम edge कहेंगे या क्या?
No, so edge की definition ये है कि it's an arrow which goes from one node to another. Okay, that's the definition. Each arrow must involve two nodes. Okay, it must start at a node and it must end at a node. That's the definition of edge. Okay.
Okay.
If you don't have any node, or if you have one single node, you can't have arrows, which means you can't have any edges. Okay. We'll see a generalization of this concept. जिसमें a node is allowed to have an arrow from itself to on itself, which is called a loop. But abhi, for now, we are assuming that there are no loops. Each edge goes from one vertex to another vertex. Okay. All right. So here is a claim that we want to prove. We want to prove the statement that the number of vertices in a binary tree is equal to the number of edges plus 1. Okay. So let's see. This is true here because 3 is 1 more than 2. 3 is 1 more than 2. 1 is, sorry, 2 is 1 more than 2. 2 is 1 more than 1, sorry. 1 is 1 more than 0. But in here it fails. It has 0 vertices, 0 edges, so it's not 1 more than the edges. So let's go back to our claim. You see the claim? The claim says that this is true for non-empty binary trees. Okay, it's not saying that this is true for empty binaries. So let's forget about the empty binary tree and let's prove it for just the non-empty binary trees. Okay, so let me write down the claim again. The claim says that for all non-empty binary trees. Actually, this is not necessarily binary को यहाँ पे लिखना ज़रूरी नहीं है. Okay. For all non-empty binary trees, the number of vertices is equal to the number of edges plus 1. Okay. So this is what we want to prove, and we will prove it using structural induction. Okay. The thing is, structural induction का जो पहला part है, which is the base case, This is proved on the base case of the definition of recursive structure. Okay, so we are doing structural induction on recursively defined structures, which means उस structure की कोई एक recursive definition होगी. उस recursive definition का जो base case है, that is going to be the base case of your structural induction. So for example, जब आपने binary tree define किया, तो this is what you said, that a root with no pointer is your base case. Okay, so let's prove the base case for a root with no pointers. Okay, this is your base case. इस case में the number of vertices is equal to 1, the number of edges is equal to 0, which means the number of vertices is equal to the number of edges plus 1, which means we are fine. This proves our base case. Is everyone happy with the base case of this structural induction proof?
सर ये बेस केस जो है एम्प्टी नोड के लिए है या एम्प्टी ट्री के लिए, मतलब इसको हम किससे रिलेट करेंगे स्ट्रक्चर वाइज अगर हम इसको देखें?
So go to the definition. जिस structure के लिए आप prove करना चाह रहे हैं उस structure की definition पे जाएं, उसका जो base case है that's your base case. Okay, so एक तो आपको you should look at the claim जो आपने prove करना है. Okay, over here the claim very clearly says that it's talking about non-empty binary trees. Okay, which means जो empty binary tree है वो तो आपका case ही नहीं है ना, that you don't have to look at. उसके लिए तो ये claim true ही नहीं है.
ठीक हो गया सर, थैंक यू.
Okay, so you go to the definition of your tree and look at the base case, and this base case, इस base case में जो कुछ भी आ रहा है, okay, हो सकता है एक से ज़्यादा चीज़ें आ रही हों, 10 चीज़ें आ रही हों, हो सकता है infinite चीज़ें आ रही हों, उन सब के लिए आपने structural induction का base case का proof देना है. Okay, यहाँ पे base case में you have a root node with no pointers. Okay, you have one root node और कोई pointers नहीं है, so let's prove it for them. So this is exactly what we do here. Okay, so it's in some sense this actually easier than the induction before, क्योंकि उस induction में मैंने repeatedly told you that base case में the critical part is to figure out what cases are included in the base case. आपने actually prove करना क्या है. Okay, that's the critical part. But this is easy because this case may they actually tell you what are the cases that you need to prove for the base case. Okay, and the cases are there in the definition. Make sense? Are we good?
Yes, sir.
Yes, sir.
Okay. This next part is probably slightly tricky. The thing is, again, ये जो आपका, so the second part is the inductive part. Okay, as before, you need to give an inductive hypothesis, and then you need to give a inductive proposition जो आपने देंगे. Okay, so again जैसे पहले था. Okay, पहले आप क्या करते थे? You prove it for pk. You show that pk implies pk plus 1. Okay, you assume this and then you prove this. Okay, that was your part. The thing is, again, this would be dictated in the definition. Okay, what does your definition say? A definition says in the recursive part that a root node pointing to non-empty binary trees is a binary tree. Okay, so root part में आप ये करते हैं कि जो recursive part use हो रहा है, okay, this is the recursive parts we are using, और इन recursive parts को use करके हम एक नया tree बना रहे हैं. Okay, so what you do is you assume the statement is true for these recursive parts. Okay, और इन recursive parts को use करके जो नया tree बन रहा है उसके लिए अपने statement को prove करना है. Okay, so शायद थोड़ा सा आपको different लग रहा हो, but let me repeat. Recursive definition में you are going to define a new binary tree using already known binary trees, right? That's the recursive definition. That's what recursion means. That already known parts को use करके अपने कोई नई चीज बनानी है. So what you are going to do in a recursive inductive step of a structure. Yeah, बोलो.
So, इसमें जो बेस केस है, it says a root node R with no pointers. Does it mean there are no pointers pointing towards it? Yeah, out of it.
There is a single root node. Okay, there are no pointers. What does it mean? There are no pointers at all. Okay, there is a single node ना, वो आपको बताया a root node, बस that's it with no pointers. Okay, yes, no. There is a single node. उसके अलावा कोई nodes नहीं है. There is a single node जिसको हम root node R कहे हैं and there are no pointers. Okay. All right, so back to the inductive step. In the inductive step, you use the recursive definition, and the recursive definition is using the already known parts to make a new structural, new recursive structure. So what you do is you assume the claim is true for the structures that we are using to construct the new structure. Okay, and then you prove it for the new structure. राइट. सो फॉर एग्जांपल इन हेयर जैसे हम यहाँ पे कर रहे थे, सो हमारे स्ट्रक्चरल डेफिनेशन में हमने ये कहा कि वी टेक अ रूट नोड, we have two pointers to two binary trees, to already known binary trees. Okay, so what we are going to do is we are going to assume that the statement is true for this guy, the statement is true for this guy. This is going to be our assumption. ओके, इस अजम्पशन के बाद हमने ये कहना है कि हमने ये जो नया स्ट्रक्चर बनाया ना, द स्टेटमेंट इज ट्रू फॉर दिस स्ट्रक्चर एज वेल. ओके, दिस इज आवर assumption and this will be our assumption. This is what we need to show, we want to show. Okay, yeah.
सर यहाँ पे जिस तरह हमने इनको एजम्पशन लिया ये नॉन एम्प्टी है, तो जो हमने बेस केस के लिए प्रूफ किया था, तो इन दोनों को, ये जो दो हैं जो जिनकी तरफ पॉइंट कर रहा है रूट,
they must be non empty.
इनको भी हम एज अ बेस केस की वजह से ही नहीं प्रूफ कर सकते, मतलब बाइनरी ट्री अगर, या ये सिर्फ केस स्पेसिफिक होगा?
देखो, the thing is, जो बाइनरी ट्री है ना, it can get very sort of I don't know, complex, right? इस तरह की कोई चीज होगी, I don't know, whatever it becomes, I don't know. Okay, so a binary tree can get really complex. Okay, but so you have to prove it for every binary tree, right?
Yes, sir.
So what we are doing is we are saying that pick any arbitrary binary tree. Okay, so let this be an arbitrary binary tree. Okay, arbitrary का मतलब ये है कि it's an instantiation of universal quantifier. Okay, pick any arbitrary tree you want. The thing is, या तो ये binary tree वो होगा जो single node binary tree है. Okay, अगर ये single node binary tree नहीं है तो this must have been constructed by the recursive definition. Okay, और तो कोई हमारे पास binary tree को हमने जैसे define किया, it's either a root or it's recursively defined by other binary trees, right? These are two possible options for this binary tree, which means that what I can say is that this guy, this whole thing, whichever the arbitrary tree was, is a root node, and there is a left binary tree, whatever it is, and there is a right binary tree. Make sense?
Yes, sir.
Okay, pick any arbitrary tree. This is what it must be. It must either be a single node binary tree, or it must be constructed by two binary trees by putting a root at the top of them. Okay, so ये वाला केस तो हमने प्रूव कर दिया. Okay, अब हम ये कह रहे हैं कि if it's constructed like this, तो फिर this is a binary tree. हम इसको assume करते हैं by inductive hypothesis. We assume the statement is true for using inductive hypothesis as well. और हम इसको prove करते हैं for the whole tree. ये हमने prove करना है. Okay, we want to show this. Okay, so what do we need to show? We need to show that so let T be arbitrary. T be such an arbitrary binary tree where T1 is left binary tree and let's say T2 is right binary tree. Okay. So what do I know? I know that the vertices in T1, let's denote them by T1. Vertices is equal to the edges in T1 plus 1. Okay, how do we know this? How do we know this fact? Yeah, no, we don't know it by base case. How do we know it? Usman Shaukat is not here, right?
Using the
Hafiz
base
Umair is there. Hafiz
Sir,
Umair?
I'm here.
Okay, how do we know this? How do we know that the number of vertices in T1 is equal to number of edges plus 1?
Sir,
Iman Ali, how do we know this?
Right, because this is a non-empty binary tree, so we just proved for the base case that for a non-empty binary tree, the number of edges, the size for the number of edges is one less than the
No,
number of vertices.
we haven't proved it. We are trying to prove it now. Mateen is there? Mateen? Haris?
Yes, sir.
Haris, how do we know this?
Sir, through the diagram, I guess, or through the base case.
So देखो, we picked a arbitrary tree, okay? और T1 उसका left subtree है और T2 उसका right subtree है.
Yes, sir.
Okay? Now I'm saying the number of vertices in the left subtree is equal to the number of edges in the left subtree plus 1. How do we know this?
Because we have three nodes in total and two edges connecting them.
No, we don't have 3 nodes. We have a whole binary tree on the left. Okay, just say for example, यहाँ पे we have a huge binary tree here. We know that the number of vertices in here is 1 more than the number of edges. How do we know this? No one? Anyone?
No, sir.
sir, we assumed it because of the
Yeah, we had
hypothesis.
assumed that this is our inductive hypothesis. In inductive hypothesis हमने ये कहा कि जो left और सब ट्री है और जो राइट सब ट्री है उसके ऊपर हमारा क्लेम ट्रू है. This was our inductive hypothesis. Yes, no?
Yes,
Yes,
sir.
sir.
Sir,
Okay. Umair, does it make sense? Hafiz Umair? Hafiz Umair is there? No? Alright. Iman Ali, do you know this? अब ठीक है, हो गया?
yes, sir.
Okay, so we know it by inductive hypothesis that the number of vertices in T1 is equal to the number of edges in T1 plus 1 because this is true by induction, inductive hypothesis. Secondly, we also know that the number of vertices in the right subtree is equal to the number of edges in this tree. Plus 1. Okay, this is what we know. So both of these statements are true by inductive hypothesis. Okay. Now we also know that the number of vertices in the original tree is equal to the number of vertices in T1 plus the number of vertices in T2 plus 1. How do we know this?
Because we have only one from else.
Yeah. So we took 2 trees and we added 1 more vertex, which means that number of vertices in the new tree is number of vertices in the left tree, number of vertices in the right tree plus 1. Okay. Number of edges in the new tree are how much? In terms of number of edges in T1
Plus T2 plus 2.
plus 2.
Plus 2.
Okay, we add 2 more edges. We add this edge and we add this edge. Awesome, great. So now we need to find out vertices in terms of edges. So let's just do that. Okay. So number of vertices in my tree is equal to number of vertices in T1. जिसके बारे में मुझे पता है कि it's equal to number of edges in T1 plus 1. Okay. So let me write it down. Number of edges in T1 plus number of edges in T2. Okay. Number of edges in T2 plus 1 plus 1 plus 1. All right. Is it clear to everyone? ये वाली equality.
Yes, sir.
Yes, sir.
Okay, so number of edges plus 1, number of edges plus 1, और ये वाला plus 1 यहाँ से आ रहा है. Okay. Okay, so now we know that the number of edges of these two trees plus 2 is equal to number of edges in the original tree. So number of vertices is equal to the number of edges in the original tree plus 1. And that makes us happy. Okay? Okay?
Okay, sir.
Awesome. Okay, so this was sort of the first example of a structural induction. What we do is we recursively define some structures, and based on that definition is the most crucial part in this type of proof. Okay, you use the base case of the definition to prove the base case of the induction, and you use the recursive part of the definition to prove the inductive step. All right, any questions? Alright, okay. क्या बोलो?
सर ये मतलब कंप्लीट प्रूफ हो गया। ये हम एक एग्जांपल स्पेसिफिक एग्जांपल के लिए नहीं कर रहे।
So हमने वन क्लेम प्रूव किया है, हमने ये वाला क्लेम प्रूव किया है। किधर है क्लेम? ये हमने क्लेम प्रूव किया। ओके, ये जो क्लेम है ना, ओके
ओके सर।
Okay, so this is not for this one example. इस example के लिए नहीं है, क्योंकि मैंने यहाँ पे आपको कहा कि pick T any arbitrary binary tree. By definition, it's either just a single node or it's made up by two different binary trees by adding a root and two arrows, right?
Yes, sir.
And we proved it in both cases. Base case भी हमने prove किया और हमने recursive case भी prove किया by using structural induction. Okay?
Yes, sir.
Awesome. All right, so that's that. Here is another one. I'm going to leave it as an exercise, but it's not that hard. So मैं शायद नीचे proof भी होगा, so I'll just show it to you. The statement is that height of a non-empty binary tree, height को हम define कर रहे हैं, okay? Definition is extremely important. मेरे ख्याल में जो कुछ हम करते हैं, definition is usually the most crucial part. Okay, there are statements के proof होते हैं, और so statements से ज़्यादा उसका proof important है, और proof से ज़्यादा definition important है. Okay, definition is probably the most important part in mathematics. I'm not sort of how do you. So the thing is, importance of definition learn करते करते it takes you decades. Okay, मुझे शायद पूरी PhD लगी to figure out the importance of definition. Okay, so I can't emphasize it enough that how important definition is. शायद I don't know if you guys पता नहीं कुरान पढ़ते हैं या नहीं पढ़ते. तो if you remember, the first thing God taught Adam was to name things, the names of things. अगर आप कुरान में पढ़ें तो this is what I get from there. That काफी देर आपको नहीं समझ आती. What does it mean? अगर कोई आपको चीजों के नाम बता दे. But that's actually the most crucial part. To name, once you name things, you start knowing that thing. Okay, so yeah, it's really important naming things. Once you have names for things, you can argue. All right, enough. Okay. Okay, I wanted to find an example which is based on sets and not trees. Okay, so ये मैंने आपको example तो बताई नहीं है. Example ये है कि so you define height of a binary tree. Height of a binary tree is again defined recursively. It says that if it's a single node binary tree, then its height is 0. Okay. But if it's not a single node binary tree, then it must be, by previous definition, combination of two binary trees and a root node. उस case में height of the tree is maximum of the height of those trees. Left वाले की height find out करें, right वाले की height find करें, उन दोनों में से जो max है वो ले लें और इसमें plus 1 add कर दें. This would be the height of your tree. Okay, so for example, अगर हम if you look at this guy, तो इसकी जो tree height होगी, it would be height of the left tree and height of the right tree plus 1. Okay, height of the left is 0, so ये height of left plus 1 होगी. Okay, that's how you define the height of a binary tree recursively. Using this formula, you can find out the height of any tree you want. Okay, you might ask the question, how do I find the height of the left tree? The thing is, now you have a recursive definition in your mind, which means you can find the height of this tree recursively again, because this guy is made up of two other trees. एक ये है और एक जो यहाँ तक आ रहा है. Okay, and so on. This is how you continue. Okay, so once you have this definition of height, which is recursive, you can compute the height of any binary tree you want. And here is the theorem that you need to prove using structural induction. It says that a non-empty binary tree of height ht has at most 2 to the power h plus 1 minus 1 nodes. Okay, so this is an upper bound on the number of nodes a non-empty binary tree can have. Okay, this is saying that you can't have 2 to the power h height plus 1 minus 1 nodes. उससे ज़्यादा nodes आपके tree में नहीं हो सकता. Okay, so you prove it for I don't know, the simplest case, which is the base case, and then you prove it recursively using this definition. It's not it's quite trivial. It's almost the same जो हमने अभी किया है.